And the second speaker is Dr. Shinji Kohara. I know Shinji for nearly 20 years, and we have spent together many hours and days of beam time at Springate, which is the most bright, high-energy synchrotron worldwide. His former beam line, BL4B2, belongs to the best instruments for studying amorphous and liquid materials, also in extreme conditions. Shinji got his PhD from Tokyo University of Science and was a very efficient instrument scientist. And now he is a principal researcher at National Institute of Material Science in Japan. He published more than 350 papers, including papers in Science and Nature journals. And he will speak about experimental work with phase change materials. Go ahead, please.
Okay, so can you hear me?
Yeah.
Okay, and the slide is okay?
Yeah.
Okay, so, okay, thank you very much for giving an opportunity to present a talk today. So title of my talk is Network Topology in Fast Phase Change Materials. So I'm working at Spring 8. Spring 8 is a very big synchrotron radiation facility in Japan. So this is a map of Japan. Tokyo is here, and Kyoto is here. Osaka is here. So this is rather west area, and Spring 8, location of Spring 8 is a little bit inconvenient. So this is Kansai International Airport. We have to take a train to Osaka and take Shinkansen, like TGV, to Himeji, Aioi, and this is not so big city, and we have to take bus to get Spring 8. This is really mountainside, and this is very big storage ring, and we have 62 beam lines, so we can perform 62 measurements at once, so together. So it's really big synchrotron radiation facility. So by the way, this is my birthplace, so not so far away from Spring 8. Okay, so outline of my talk is here. So first of all, I would like to introduce PDF. PDF is paired distribution function. PDF analysis on glassy, liquid, and amorphous materials. It's very short introduction. Oops. Okay. Oh, and of course, we typically use X-ray diffraction, and sometimes we use neutron diffraction, because neutron diffraction is very sensitive to light elements, particularly oxygen atoms. So, because I recently work with oxide materials. So, okay, after that, I would like to introduce how we can understand diffraction patterns of glassy, liquid, and amorphous materials. And we recently introduced persistent homology analysis. This is rather new topological analysis tool on the basis of mathematics. So, of course, we need atomic configuration to perform this analysis. And then I would like to move on to the last topic, so phase change materials. Actually, I worked with Bob, previous speaker, for a long time, but mostly 10 years ago. So we combine measurement and DFMD simulation, and we published a joint paper, so several joint paper. And okay. First of all, I would like to introduce typical diffraction from glassy, liquid, and amorphous materials. So this is our dedicated diffractometer for the measurement of PDF of glassy, liquid, and amorphous materials. So first of all, I would like to introduce the difficulty in solving the structure of disordered materials. Okay, this figure shows X-ray diffraction pattern for germanium dioxide. So red line shows the crystalline data, and the blue curve shows glassy data. So this is normalized data. So we typically use a scattering vector instead of scattering angle. So this is normalized by wavelengths of X-rays or neutrons. So this is Q space data. And also data is usually normalized to structure factor. So this is normalized data. Okay, so in the case of crystalline phase, we can observe very sharp black peaks because crystalline phase has very well-defined periodicity. On the other hand, glassy phase shows very, very broad, so-called halo pattern. So we typically fully transform this Q-space data to real space, where we can assign pair correlation. This is a total correlation function, but some sort of PDF, so just different formalism. And the first peak can be assigned to germanium oxygen correlation. So because in both crystalline and glassy phases, short range structure is germanium GeO4 tetrahedra. And this is corner shared and oxygen. So with sharing oxygen atoms at the corner, this is corner sharing motif. And this is germanium oxygen correlation peak. And if we integrate the area, we can get a coordination number. Coordination number of germanium oxygen atoms around germanium is 4. This is tetrahedra. And okay, this real space data, red curve shows crystalline phase and blue curves shows glassy phase. But up to 4 angstrom, so they are very similar because they are tetrahedral configuration with corner sharing oxygen, same tetrahedral motif. So up to 4 angstrom, they are very identical. However, over 4 angstrom, crystalline phase still shows significant oscillations due to periodicity, but in the case of glass, it is very broad and not so much information at a long distance region. So this is very difficult point in glassy materials because there are almost no long range periodicity, and we can describe in only averaged pair correlation. And in addition, we don't have no dedicated descriptor like space group or space group or lattice constant. So this is a difficulty in glassy materials. So we need a comprehensive integration of experimental, theoretical, and data-centric science. So this is very important collaboration. So measurement, theory, and probably data science. Okay, so let me introduce our recent paper published in Japanese journal. So we combine diffraction measurement, simulation, and topological analysis, persistent homology analysis. I will introduce later. So this figure shows several structure factor of several disordered materials. So some data is X-ray. This is X-ray and neutron. So blah blah blah. And this is very important and typical amorphous material. Amorphous silicon, and these materials are tetrahedral and almost corner sharing motifs. So this is silica, germania. They are very, very good glass forming materials. Germanium sulfide selenide, they are very good glass forming material. Zinc chloride, not so good. But of course, we can get glass C phase by using conventional melt and quench method. But this is more ionic. This is really very, very covalent. And covalent bond shows very sharp, so-called fast sharp diffraction peak. So this is silica germania. They are very, very strong covalent network. And zinc chloride, very, very ionic. But in the case of amorphous silicon, we cannot observe fast sharp diffraction peak. Oh, by the way, we scale Q by multiplying short range, closest distance. So this is just the center of tetrahedra and the corner of tetrahedra. This is center and corner distance to eliminate the size of atom. So then we can classify these three peak structure in silica, germania, and yeah, these are tetrahedral motif. But we cannot see such a FSDP in amorphous silicon because amorphous silicon doesn't have large fraction of empty space. They have very, very relatively large fraction of empty space due to two-hold oxygen or sulfur, selenium, and chlorine. So this is 4-fold and 2-fold, so which gives a relatively large fraction of empty space. We call cavities. So in silicon, everything is 4-fold. So we cannot see fast sharp diffraction peak. But fast sharp diffraction peak is observed in molecular liquid. So this is liquid phosphorus. This is tetrahedral, but there is no center atom. But carbon tetrachloride, carbon should occupy the center of this tetrahedra. And carbon is surrounded by four chlorine atoms. But they are isolated, no sharing. This is isolated tetrahedra. Nevertheless, we can observe fast sharp diffraction peak. So from this figure, we can reasonably conclude that fast sharp diffraction peak is not a signature of network. They are network forming materials, but carbon tetrachloride, phosphorus, they are isolated molecular liquid. But we can observe fast sharp diffraction peak. This is very important comparison. Okay, so this figure shows a comparison between neutron diffraction and X-ray diffraction data for silica glass. Silica is the most famous glass forming materials. So, and this is neutron and this is X-ray, and blue is experimental data. And the red curves show combined molecular dynamics and reverse Monte Carlo modeling. So very good agreement between experimental data and model. So in both diffraction data, we can observe fast sharp diffraction peak. So almost the same Q position. However, second principal peak can be observed only in neutron diffraction data. We cannot see such a peak in X-ray diffraction data. So I'd like to explain the reason why. So this is partial structure factors obtained from the model. So this is silicon, 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 oxygen, and oxygen, oxygen. 3 partial structure factors and already multiplied neutron weighting coefficient. So this is simple summation of 3 curves exactly same as this red curves. So this is X-ray case and this is neutron case. Original partial structure factors are same for both, but weighting factor is different between X-ray and neutron diffraction data because X-ray is more sensitive to heavy element. So silicon, silicon weighting factor becomes large. On the other hand, in neutron diffraction, oxygen, oxygen correlation is very, very sensitive. So because oxygen atom is very sensitive, very easy to probed by neutron. So oxygen-oxygen correlation peak becomes large in neutron diffraction data. And actually, principal peak is just a summation of 2 positive peak and 1 negative peak. So weighting factors are different in both in X and neutron data, and so we can observe only in neutron data a principal peak. Principal peak can be visible in only neutron diffraction data because this peak represents the oxygen-oxygen correlation. So original structure is the same, but diffraction patterns different. This is very important point, and that's the reason why we combine both neutron. We combine neutron and X-ray diffraction data to study disordered materials because information is insufficient in principle for disordered materials. Okay, so we have been working on the origin of the FSDP, why we can observe fast sharp diffraction peak. So we can roughly estimate periodicity and correlation length by analyzing FSDP. This is a position of FSDP. This is a width of FSDP. So we can estimate periodicity is almost 4 angstrom and the correlation length is 10 angstrom. So periodicity is represented by this cyan curves. This distance is almost 4 angstrom. So this is I picked up the configuration from the model, and we just removed atoms which don't belong to network. So this is very simple illustration, but of course on the basis of simulation. So, and the correlation length is 10 angstrom. This is almost 10 angstrom, just 1, 2, 3, 4 layers. This is a correlation length. So this is very, very sparse configuration. And this is the origin of fast sharp diffraction peak. And this slide visualizes cavity distribution in silica glass using cavity calculation code developed by Ulrich scientists. Bob is also involved in the project of this code. And in our analysis, cavity volume ratio is almost 32% in silica. So silica has a large fraction of empty space. So this is a very, very typical atomic configuration for good glass forming oxide materials. And this slide shows ring statistics. So in this analysis, we define 6-hole ring consists of 6 tetrahedra because this is silicon. No, this is silicon. Because silicon, oxygen, silicon bond angle is nearly linear, almost 100, not 180, but more than 140. So looks like linear. So we call 6-hole ring this configuration. And in cristobalite, this is a crystalline phase of silica whose density is comparable to glassy phase. In cristobalite, we can find only 6-hole ring. But in glass, we can see the variation of ring size. Although 6-hole ring is dominant. But according to Cooper and Gupta, this is topologically disordered. This is topologically ordered. And this topological disorder is an important feature in glass. This is their conclusion. So this is very important contrast between glassy phase and crystalline phase. And I would like to mention a little bit about the origin of principal peak. This is principal peak. So this is state-of-art neutron diffraction data under high pressure are reported by Samo and Zeidler. So this is in situ high pressure data. And if we increase pressure, we can observe diminishment of FSDP. But instead of this diminishment, principal peak becomes very, very sharp. And principal peak is reflects the oxygen correlation. And this sharp principal peak reflects increased packing fraction of oxygen atoms under high pressures. So this is very, very important signature and behavior of glassy materials under high pressures. This is very important data. And of course, this modification is associated with a reduction of cavity volume, as shown here. This is really densified silica. Of course, short range structure remains the same, tetrahedra with corner sharing motif. But just a reduction of cavity volume, we can see very, very obvious change in diffraction patterns. Okay, so I would like to compare diffraction data for various disordered materials. This is very, very important comparison, at least for me. So this is metallic glass, copper zirconium glass. I think this is structure of metallic glass is rather similar to antimony tellurium alloys in phase change materials. Very dense pack structure. So we can not observe FSDP nor principal peak because very dense pack. But in amorphous silicon, we can observe principal peak, but no fast sharp diffraction peak. And the silica and the carbon tetrachloride, they have 3 peak structure. So, and also we also plotted colloidal PMMA. This is some sort of hard sphere, but a very big hard sphere. However, if we scale the cube by fast correlation distance in real space, so very, very similar shape, colloidal PMMA and metallic glass. They are really hard sphere model. So in which we cannot see obvious chemical bond. But these guys have more chemical bond. So silicon and silica, carbon tetrachloride. Okay, so this slide shows atomic structure and average coordination number. This is carbon tetrachloride, silica, silicon, and copper zirconium, metallic glass, dense random packing. So coordination number is almost 12. Very, very dense packed structure. In amorphous silicon, coordination number is 4 because every silicon atom has 4-fold. And in silica, silicon has 4-fold and oxygen has 2-fold. So average 2.67. In carbon tetrachloride, tetrahedra is isolated. So coordination number of chlorine around carbon is 4, but coordination number of carbon around the chlorine is 1. So average 1.6. So this is really sparse, but this is really dense, almost no cavity. So let's get back to structure factor again. And so from this comparison, this atomic configuration and the coordination number and diffraction data, so we can reasonably suggest that FSDP and principal peak, they are signature of sparseness. So if structure is dense packed, we cannot observe FSDP nor principal peak. So this is very important comparison. Dense random packing and molecular liquid network glass with this is a fully 4-fold network, but this is glass has chemical contrast. Silicon is fourfold, oxygen is twofold. So they are very different network motif. So this is okay. Just this is very general argument. Is FSDP a descriptor for network? So as I mentioned in the beginning of my talk, so this is no. FSDP is not a universal feature of glass network. I think FSDP is a signature of sparseness with the arrangement of plane in polyhedra, probably. Formation of orientational correlation is very famous in carbon tetrachloride. So this orientational correlation is very important because principal peak is not single peak, doublet. This is due to the mixture of different orientational correlations in molecular liquid. So this is a little bit exceptional, this doublet principal peak. And another important point, if we compare first sharp diffraction peak of silica glass with carbon tetrachloride, obviously FSDP is much sharper in liquid. Glassy phase, very broad FSDP in comparison with carbon tetrachloride. So, but how we can understand so liquid and glass completely different, but FSDP is very sharp in liquid. So let me discuss later this topic. Okay, so this is very simple cartoon, just a modification from silica to silicon. This is an atomic configuration of silica. So I want to make silicon from silica. How we can make silicon? So we just replace oxygen atoms by silicon atoms, like this. But silicon should be fourfold. So we have to add more silicon atoms. Okay, then empty space is disappeared. So that's the reason why FSDP disappeared in diffraction data. So this is a very, very simple cartoon to understand why FSDP is not observed in amorphous silicon. Okay, finally, I would like to discuss Q principal peak and Q3. This is Q2 principal peak. We can observe principal peak in amorphous silicon because coordination number of amorphous silicon is 4, still very much lower than metallic glass. So amorphous silicon has much more empty space in comparison with metallic glass. That's the reason why we can observe principal peak. Yeah, but fourfold coordination is a result of inherent chemical bonding, which is not observed in dense random packing structure in metallic glass. So I think this principal peak is a signature of the formation of chemical bond in amorphous phase. And finally, Q3, according to Samo and Zaidler, Q3 seems to appear as a result of the repeat of nearest neighbor correlation. I would like to simulate this point by reverse Monte Carlo modeling. I would like to introduce a little bit about reverse Monte Carlo modeling. I think this is some sort of data science because this is really data-driven modeling, and this is data science. So in RMC, so we can provide a 3-dimensional atomic configuration which is consistent with given diffraction data. Okay, I'd like to explain simple algorithm. So this is really Monte Carlo procedure. So choose an atom in the simulation box at random and move at random. Then we calculate chi-square with experimental data. And if chi-square decreased, so the movement is accepted. If not, this movement is rejected. But if we simply follow this this approach, I think movement is stuck. So if agreement is not improved, we have to accept some sort of movement. This is really Monte Carlo. So, and just repeat this simple procedure until calculated data agree with experimental data. So this is some sort of energy evaluation in conventional simulation method. But in RMC procedure, this is replaced by a chi-square with given diffraction data. This is just a cartoon of RMC. Target experimental data is G over R, shown as blue curve. This is a initial configuration, red curve. And atomic structure is very well ordered, so very sharp peaks, even in real space. Then we start RMC. So structure becomes disordered, and finally, we can reproduce given experimental data. So why we call reverse Monte Carlo? Because we have answer from the beginning, because answer is this experimental data. So to construct model to reproduce given diffraction data, this is the reason why we call reverse ahead of Monte Carlo. So this is very very quick, but sometimes very dangerous because RMC doesn't know any chemistry or physics. So we have to be careful to perform RMC modeling. Okay, this is target data, structure factor, liquid mercury. Liquid mercury is some sort of random dense packing. So coordination number is almost 12, same as metallic glass and antimony tellurium alloy. So we have experimental data and Fourier transform. But in this RMC, we use only G over R data up to 4 angstrom, very, very limited data. And then we run RMC. But we can reproduce this Q3 peak with only this limited information. So that's the reason why we insist that Q3 is a result of the repeat of pair correlation. So this is very simple check. Okay, so in my talk, we introduce the scaling of distance of the center of tetrahedra and the corner of tetrahedra. This is our formalism. But very recently, Professor Tanaka proposed formally normal scaling by center of tetrahedra with center of tetrahedra. And this is the result. I think this is a little bit strange for me because just we compare. So this is our not only me, many diffraction scientists scaled by center and the corner of tetrahedra. This is conventional way. And comparison between amorphous silicon and silica. So we can conclude no fast sharp diffraction peak in silicon. But in Tanaka's form scaling, amorphous silicon shows FSDP. This is their conclusion. This is our conclusion. So I would like to ask you, which do you like better? So this is interesting argument, but we can see very good similarity between silicon and silica data, except FSDP. It's very different. Okay, anyway, let's move on to next topic. Probably I talked too much. And okay, I would like to introduce persistent homology analysis. In this analysis, we need atomic configuration. So we put results of simulation, DFMD or classical molecular dynamics and reverse Monte Carlo. And then we can get a persistence diagram. This is a persistence diagram for silica glass. This is lots of empty space. This is a metallic glass, but only zirconium. So in network structure with large amount of empty space, we can observe very, very sharp profile along with the death axis. And this is a signature of network. And in the case of metallic glass, very, very strong profile, but this value is very, very small. This is typical metallic dense packed structure. Okay, I would like to mention how we analyze data. Very simple. Okay, we just increase radius of ring particles. Just increase, 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 and then we found rings. This is a point of birth. This is birth value. If we find ring, and so we find ring X at birth 1 point, and then increase more and more, and we find ring Y at birth 2, and then increase more. Ring Y disappeared at death 2. This is death. And if we increase more and more, ring X disappeared at D1. And then we repeated this analysis for all particles, and we can illustrate this diagram. This is birth and death. So this small birth death value means very short lifetime. So ring is distorted or very small. And if death value is very, very large, ring is large or very, very good symmetry. So this analysis can analyze not only ring size, but also shape of ring. This is very powerful tool, and we should combine with conventional ring statistics analysis. We actually introduced this method for silica polymorphism. So this is glassy silica, and this is crystallite, quartz, quartzite. They are tetrahedral with corner sharing, but density is very different. This is lower density, and this is highest density, tetrahedral corner sharing, crystalline phase. And this is glassy phase. Density is almost 2.2. This is probably 2.7, and this is 2.9. This is 2.3. They are comparable density. So first of all, I would like to show you ring statistics. This is 6-hole ring I showed before. And this is typical for crystallite. In quartz, we can find a large fraction of 8-hole ring. But in the case of quartzite, there are various ring sizes. It's really topologically disordered, even for crystalline phase. So this is almost, I think this is between crystalline phase and glassy phase. Even though this is crystalline phase, but this is some sort of disordered crystal for me. This is glassy phase, and this is persistence diagram for silicon atoms, silicon-centric persistence diagram. So this is a very characteristic profile along with the death axis. This is a signature of disordered network. And in crystalline phase, it's important. Crystallite has only one profile, and this value is very large because this 6-fold ring should be very, very symmetrical. So very, very long life profile. This value is very large. But in quartz, this value becomes small and quartzite smallest. This is a different. Okay, important point. In quartzite, we can see large fraction of large ring. However, very short lifetime, which means that ring is very backward. So very, very asymmetrical, very funny shaped rings in quartzite. So another important point, silica glass has silica glass has a very, very broad profile covering coesite to cristobalite. This is really important information. So glassy phase has three topology in three different crystalline phases. This is really important feature in silica glass. Okay, I would like to skip and let's move on to next phase change material. Okay, so let's move on to next topic. This is phase change material. Okay, this slide shows the mechanism phase change in DVD and Blu-rays. When we buy raw media, this is crystalline phase. And crystalline phase has a high photoreflectivity. And of course, crystalline phase shows long-range ordering. When we want to record the data, we just give a very short laser irradiation, so only 20 nanoseconds. But temperature is greater than 650 degrees centigrade. Then crystalline phase rapidly transform to amorphous phase via liquid phase. And this is a recorded phase. And amorphous phase is transparent to laser, so photoreflectivity becomes lower than crystalline phase. And this difference in photoreflectivity can recognize data. So this is a recorded mark. This is amorphous phase, some small mark. This is amorphous mark for DVD RAM developed by Panasonic. And this is, this mark means this is lower density. So volume becomes large in amorphous phase. So this is very important. And this is recorded mark for DVD. In the case of Blu-rays, probably this size should be 20% or something, because density is much higher in Blu-ray. So that's the reason why we need blue laser, because we can focus beam size of laser in Blu-ray. So if we buy Blu-ray player, we have two laser systems. Red laser is for DVD and blue laser is for Blu-ray. So important point is erase process from amorphous phase to crystalline phase. Again, we need very short laser irradiation. However, very short time, again, 20 nanoseconds. But temperature is very low, and less than 200 degrees centigrade. But nevertheless, amorphous phase can transform rapidly to crystalline phase. So actually, Panasonic people, they are interested in this first erase process. But this erase process is important for only rewritable media. But unfortunately, rewritable media is not so commercially successful, because most of people do not care too much about rewritable media, only some Japanese. So it is very, very good. GST225 is very good material and used in only DVD RAM developed by Panasonic. But unfortunately, not commercially successful in Japan. It's very pity. But we are interested in very fast crystallization process. And Panasonic people, as Bob introduced, we have been working with Yamada-san and Matsunaga-san, Panasonic. So very simple question. Why amorphous phase can crystallize rapidly despite it is so stable for a long time at room temperature? This is a little bit paradox problem. And to answer this question, we started collaboration. As Bob introduced, we have two commercial phase change materials. This is GST, pseudo-binary system, germanium telluride and antimony telluride. This is alloy system. AIST, we call it AIST. So mostly antimony and tellurium alloy. And phase change mechanism is different, as Bob introduced. But important point, this is really something like metallic glass in my previous topic. So very dense packed atomic configuration. But this is much more covalent and network, and the structure is rather similar to oxide system. But this is really dense packed structure, and the coordination number is much higher than this covalent system. These are very important difference between GST and AIST. And this is a collaboration with Bob. And we found that in GST, we found large fraction of the fragment of crystal as nuclei. This is we picked up from the configuration of DFMD simulation. We can see some sort of fragment of rock salt lattice, and also this is AB, germanium or antimony. Germanium and antimony is A, B is tellurium, AB square, some sort of network, covalent network. But in AIST system, we found distorted 3+3 octahedron in amorphous phase, and this is schematic transformation from amorphous phase to crystal phase. This is very different features in GST and AIST. This is really metallic for me. This is more covalent network. So I would like to focus on this GST material. Okay, so as Bob introduced, crystalline phase has a rock salt structure. This is actually metastable phase. So, and lots of vacancy, as Bob introduced. And crystallization behavior is, we can observe lots of nuclei. So, okay. First of all, we have performed, of course, diffraction measurement, and this is crystalline phase, and this is amorphous phase. This is black peaks, but there are significant diffuse scattering, so very distorted crystalline phase. And this is amorphous phase. So we assign first 3 peaks, first sharp diffraction peak, principal peak, and Q3. And first sharp diffraction peak is not sharp because this material very, very low amorphous forming ability. We cannot get bulk materials. We can obtain only thin film. So that's the reason why FSCP is not so sharp and not so obvious. And then we fully transform to real space function. It is very important point. First peak position is very, very different. So this is overlap of germanium tellurium correlation and antimony tellurium correlation. Bond distance is very, very similar, and we cannot distinguish which is which. And this is crystalline phase, and this is amorphous phase. In the case of germanium dioxide, first up to 4 angstrom, they are identical, but in phase change material, they are very different. Nevertheless, very fast phase change. And of course, germanium dioxide, not so fast phase change material, but unfortunately, we cannot find out any similarity in short range structure. This is no obvious signature for rapid phase change. If we take a look at fully transformed data. But the important point, position of first peak is different. And in amorphous phase, coordination number is almost 4-fold. But in crystalline phase, coordination is 6-fold. So short range structure is completely different. But phase change is very fast. So it is necessary to analyze atomic structure beyond the first coordination distance. Okay, and this is very old paper, 2006, and this is not so good quality reverse Monte Carlo modeling because this GST contains germanium, antimony, tellurium, 3 atoms. So we have 10 partial configuration, partial structure factor, but we have only one experimental data. So there are, this solution is not so unique. So, but anyway, we tried in 2006, and we found a large fraction of four-fold ring. In this case, four-fold ring is formed by only 4 atoms, very different from silica case. So we found a large number of four-fold rings. This is rock salt lattice. And as Bob introduced in his talk, 2007, they also found a large fraction of four-fold ring. So they are very good, reliable DFMD predict the formation of large number of four-fold rings too. So conclusion is almost the same. But Bob and we compared our configurations. So first of all, we calculated the structure factor from DFMD simulation. This is experimental data, and this is the results of DFMD simulation. Agreement is not so good as RMC. Of course, this is theory. So, and in particular, so first correlation distance in real space is different. I think this is just 2007, and I think probably simulation is much improved now. Yeah, anyway, so in my mind, DFMD cannot reproduce covalent bonds in amorphous phase. And Bob calculated density of state from our model. And it is very lavish density of state because we cannot observe a band gap in RMC model. This is quite reasonable because in RMC model, so this blue curve, bond angle is very, very strange in comparison with DFMD. So this broad bond angle distribution is a reason for metallic behavior. So because in diffraction data, we don't have any information for this triplet correlation. So then we try to combine two simulation method. So approach is very simple. They performed DFMD simulation using a supercomputer, and then we put configuration to RMC to reproduce X-ray structure, X-ray diffraction data. But important point, we provided very strong constraints, coordination numbers obtained by DFMD simulation, and also we applied bond angle distribution. This is very important point to avoid very funny density of state. So after that, Bob and Yako performed DFT calculation to calculate the density of state and blah, blah, blah. And I would like to show you final combined RMC DFMD model, so we can get good agreement between X-ray diffraction, blue curve, and magenta combined RMC DFMD model. And also, important point, total energy of our final model is only 0.079 eV per atom, higher than that of the original DFMD model. Very small difference in energy. And also, we can observe band gap here. So this is a most reliable model. And again, we calculated ring statistics, and we found large fraction of four-fold ring in our most reliable model. So four-fold ring is a very important feature in amorphous phase. Sodium rock salt lattice. But we have a new question. So now we cannot distinguish antimony and tellurium in X-ray diffraction data because atomic number difference is very small, only 1. So we cannot distinguish by normal X-ray diffraction technique. However, we want to know the role of each element for ring formation. then we need element-specific technique for diffraction measurement. Then we performed anomalous X-ray scattering measurement by using synchrotron X-rays. In this measurement, by tuning the energy of X-rays, we can distinguish between antimony and tellurium beyond the first coordination distance. Only first coordination distance, we can perform exact measurement, but we need information beyond the first coordination distance because first coordination is very different between amorphous and crystalline phase, and we need similarity between both phases beyond the first coordination distance. That's the reason why we performed anomalous X-ray scattering. This is antimony specific data, and this is tellurium specific data. They are slightly different. Okay, I will skip. This is too much detail. This is too much detail. And anyway, by utilizing anomalous X-ray scattering measurement, we have another two diffraction data. This is antimony and something. Antimony, tellurium. Antimony, germanium. But there is no tellurium, no germanium, tellurium in this data. And this is tellurium specific data. There is no germanium, antimony in this data. They are not the same. And we applied a DFMD model to 3 data sets. And we reproduce 3 different diffraction data. And then we are back to ring size distribution. Of course, 4-fold ring is still dominant. And this is, okay, this is only germanium tellurium ring. And this is antimony tellurium ring. And by this analysis, we found germanium tellurium form large fraction ring, and antimony tellurium doesn't form ring. By this analysis, germanium tellurium is a network former in terms of ring formation. So yeah, germanium tellurium bonds form 4-fold and 6-fold ring, but antimony tellurium bonds do not form ring. So next, we performed the persistent homology analysis. This is germanium antimony site. This is tellurium site. This is crystalline phase, and this is amorphous phase. It is an important point. They are very similar. Persistence diagram. This is crystalline phase, and this is amorphous phase. This is very, very different from amorphous silica because amorphous silica doesn't have such a similarity between class C phase and one specific crystalline phase. But in this phase change material, they are very, very similar. Topology is very similar. So both phases shows similar topology. This is very important information from persistent homology. But important point, this is not good glass forming material. So it is natural that behavior is very different between silica and GST. Okay, so we have performed much more connectivity analysis for germanium tellurium bond and antimony tellurium bonds. So because we want to analyze continuous connectivity hidden in pair correlation, we cannot distinguish by pair correlation because very limited information. So for instance, we cannot make sure 4-fold ring is isolated or 4-fold ring forms a network. So to distinguish, to make sure this point, we performed connectivity analysis for germanium tellurium and antimony tellurium correlations. So this is a ratio of continuous connectivity. In germanium tellurium case, so if we assume first coordination distance up to 3.2 angstrom, this is suggested by DFMD simulation, we can find a network because almost 60% of germanium tellurium bonds form network as shown here. But antimony tellurium, up to 3.2 angstrom, there is no network. However, if extend this threshold distance up to 3.5 angstrom, we can find network. But this is not network because distance is greater than first coordination distance. So we call this is pseudo network in antimony tellurium. So now let's discuss the role of antimony in the crystallization of amorphous phase. If we consider correlation distance up to 3.2 angstrom, there is no network by antimony and tellurium. They are almost isolated. But if we increase the distance up to 3.5 angstrom, so we can find pseudo network. So this pseudo network makes it possible to transform rapidly into antimony tellurium bonds via laser irradiation. So very rapid transformation from amorphous phase to crystalline phase. So I would like to conclude this talk. So in GST phase changing materials, so we can reasonably conclude that germanium tellurium bonds form covalent network to stabilize amorphous phase and also sustain crystalline topology by the formation of network. And antimony tellurium correlation form pseudo network. I think this is a reason for fast nucleation. So we have succeeded in uncovering the reason for the stability of the amorphous phase and that for fast crystallization by element-specific structure analysis. Okay, thank you for your attention.
Thank you very much for your nice talk. Now it's paper open for discussion. Yes, please.
I have a question about the first sharp diffraction peak. You could see your results there comparing silicon and silica, that the cavities of the empty spaces played a role. Now, there was a paper by Stephen Elliott in 1992 on the origin of the first sharp diffraction peak, and he claimed it was due to ordering of the vacancies. But I didn't hear that from you. I mean, what do you think of that? I mean, you don't believe it?
Yeah, but this is my opinion. So
yeah,
vacancy doesn't provide any diffraction peak because there is no atom. But I think around vacancy, there is a network by silicon-oxygen.
Yeah.
So probably this atomic arrangement is the origin of first sharp diffraction peak. So void is not a direct reason, but indirect reason, because atomic arrangement around voids is the origin of first sharp diffraction peak. This is my opinion.
Okay, but the question is does the order, he focused on the order, that in other words, these empty regions were somehow ordered. This was his explanation of it in 1992. It's a long time ago. But you don't, I don't see anything in your argument which suggests they might be ordered.
But Chris Benmore and co-worker, they calculated Bartius-Thornton partial structure factor, and they concluded to rule out void model by his analysis. So yeah, but I think void is very important.
Okay.
I have a comment about it. The biggest first sharp diffraction peak is the molecular liquids.
Yeah.
Where in principle, position of the peak is average intermolecular distance. It's proportional to the average intermolecular distance. if you just take the value of FSDP in Q space, you divide 2 pi by Q, you will get roughly intermolecular distance, which you could find quite easily. So I guess it shows that there is no simple explanation. It may be for different materials, origin could be a little bit different. In molecular systems, it's one. In a network systems, it could be a little bit different, etc.
Yeah, but for instance, potassium lead. In potassium lead, we can find tetrahedral by lead, 4 lead atoms. This is really looks like molecular, but this, according to David Price, they called fast sharp diffraction peak. Yeah, so of course origin is probably not exactly same because molecular liquids no network, but silica has network.
Yeah.
But in my mind, why FSDP of carbon tetrachloride is so sharp? Probably arrangement of tetrahedra has freedom in molecular liquid in comparison with network, because in the case of network, tetrahedra is constrained by the formation of network. So there are no freedom. But molecular liquids, much more freedom. That's the reason why correlation distance becomes long, even in liquid phase.
Yeah.
This is my opinion.
Shinji, I have questions. So you have shown 3 peaks, FSDP, PP, and the third peak. Yeah. And you show that if we take metallic glass, which is random dense material, we do not have neither a first sharp diffraction peak nor PP. We have only a third peak. If we take, let's say, SiO2, and you apply pressure, so you will progressively make more dense structure. And for example, if you are going to 200 GPa or something like that, what will happen with structure factor? FSDP will disappear, it's clear. Whether PP will disappear.
PP is no, still survive, because very high pressures, principal peak becomes sharp due to increased packing fraction of silicon atom. Because in the case of tetrahedral motif, packing fraction of silicon atom is same, because silicon has 4-fold. But under very high pressure, silicon is 6-fold. So packing fraction of silicon atom becomes large. So evolution of principal peak is visible in X-ray data, which means that silicon packing fraction is increased, because oxygen principal peak is visible in only neutron diffraction data. But in X-ray diffraction data, if we go greater than 100 GPa, we can observe evolution of principal peak. This is due to not increased packing fraction of oxygen atom, but silicon atoms. So this is a behavior under very high pressure.
Okay. I have another question. When you are talking about phase change materials, you apply short laser pulses, and to get amorphous structure, you mentioned the temperature 650 C. It was measured, or it was some kind of estimation? What temperature you have?
Estimation.
From what?
This is the estimation.
And from what this estimation, and whether you suggest it will be some pressure, because you hit some solid material with a focalized laser beam. It's hit locally. around this place, you have material at room temperature. Let's say we forget for the moment about dissipation of heat. So in fact, in this particular place, you will have high temperature and high pressure because your volume is limited. How could you, did you try to estimate temperature and pressure in this particular region?
Only temperature, they calculated. Panasonic people calculated temperature, and they confirmed surely greater than melting point. They concluded, but not pressure.
And on what was based this estimation? How it depends on beam, laser beam power? Energy.
Yeah, and probably they calculated heat transfer and heat loss and something. I don't know detail, but I asked the Panasonic people. I don't know in detail, unfortunately.
Okay. I have also a question to Bob about this process. When you analyze crystallization or amorphization, you also talked about temperature about 600, I forget, Kelvin or Celsius. Kelvin. What is the basis of this temperature?
Well,
whether you took atmospheric pressure or you consider some higher pressure?
Okay, what the calculation is done, we take the density of the material as measured, and we fix our unit cell. In other words, it is a constant volume unit cell.
Okay.
Of course, the pressure is certainly there. We do these simulations at a series of temperatures, 700, 600, 500. At lower temperatures, not much happens, and so that you have to wait longer. And 600 degrees was reasonable. It's quite a long way below the melting point, but it's still enough where things are happening. But we have done simulations at 700, 600, 500, and so on. And at low temperatures, nothing much happens in our simulation. And so we need things to happen. And there is certainly pressure in the sample because we do not have a pressure equal to 0. We have a constant volume, and the density is then fixed by experiment.
Okay. Thank you very much. Any more questions to?
I have one question to Dr. Kohara.
Mm-hmm.
Do you hear me? Could you please comment on persistence diagram?
Persistent homology, you mean?
No, persistence diagram that Dr. Kohara was talking about. I couldn't get what is the unique thing with this persistence diagram, because on the RIN statistics you can see the same thing, same specific for glass, same specific for crystal, but what is the thing for persistence diagram? Why should we use it?
Okay, so okay, I'd like to show this slide again. So important point, ring statistics cannot tell us the shape of ring. Ring is very symmetrical or not. For instance, these data, these data, they are just a size of ring, no information about shape. But for instance, cosite, okay, crystallite case is very simple because density is very low. So 6-fold ring and base is very large, which means that 6-fold ring is very symmetrical. If 6-fold ring is buckled, probably this volume should be small. this logic is very obvious in co-site. In co-site, really topologically disordered, 4-fold, 9, 10, 11, 12. This is very big, large ring. Nevertheless, this is not so large. This is not so large. This means that this 12-fold ring is very buckled, significantly buckled. For instance, probably this 6-fold ring is this is not 8. Yeah,
So
very
this can
small.
show the emptiness. This can show the emptiness of the structure. So are there any empty places in the structure or not using this diagram?
Yeah, obviously co-site very high density and not so much empty space, and that's the reason why ring shape is very distorted, and this value is very small. So this is very large, but very distorted. That's the reason why we cannot see large this value in co-site. This 12-fold ring is very funny shape. I don't have a real configuration now. I cannot show now, but very twisted. Ring is very twisted.
I got it. Thank you.
Any more questions, please?
May I ask a short question? But this question will maybe consist of 2 parts, but that's okay. Could you show the first, maybe second slide of the second presentation, where you started to discuss temporal, some change in dynamics from different, in the beginning, just in the beginning of this. Okay, the second slide. No, one more back. Okay, this one. Okay, so you from crystal you are discussing the liquid phase, and then you have amorphous phase and back. Which of these processes could be light induced, and if it's possible, could be reverse light induced process in this diagram?
Sorry, I can't understand.
What other light induced process could take place from the transformation from liquid to amorphous, or liquid from amorphous to the crystalline, and maybe back? Which of them could be light induced?
This is a crystalline phase, no data. This is a lighting process.
Lighting.
Yeah, recording means lighting. And
So
this is
from crystal, you may transfer the system to the amorphous by light.
Amorphous phase is transparent against the laser, but crystalline not transparent.
I mean the transformation from crystalline to amorphous by laser pulse. Is it possible or not?
Transformation.
Phase transition.
From which to which?
From crystal to amorphous.
Crystal to amorphous. Oh, I see. Okay, this is a very big argument, and because some people pointed out just a simple crystal to amorphous transformation without liquid phase. Without
liquid.
Yeah, that's the reason why Panasonic people are interested in the estimation of temperature during laser irradiation to the crystalline phase, this process. And they confirmed the temperature is higher than melting point. And then we concluded that crystal into liquid to amorphous. This is our conclusion. But many people thought just a simple crystal to amorphous transformation. but we don't think so.
Mhm.
But of course, there are some argument in
Some
10 years ago. Yeah. But
Okay, the second part of
some
this
sort of photo assist transformation could be, but in our phase change materials, liquid phase, crystalline liquid amorphous, and not reverse cycle. Our conclusion is cycle, not reverse process. This is our conclusion.
Mhm. So the second part of this question. Okay, you have crystalline phase of the substance, crystalline, the first one. Then you heat it up to 650. You have liquid.
Yeah.
Then after liquid, you have amorphous phase because you are cooling. Cooling more down, you have crystalline again. If it's liquid on the way, it should be always very slow. Is it possible to avoid heating to transfer from crystal to amorphous?
Crystal to amorphous.
Without heating.
Without. We don't think so.
We don't think so.
Yeah, but this is a big argument 10 years ago. Yeah, some people believe, yeah, crystal to amorphous, no liquid phase. But Panasonic and I concluded no. No liquid. We need a liquid phase, crystalline liquid amorphous, no crystalline amorphous. This is our conclusion.
Okay, thank you very much. Thank you.
Any more questions, please?
May I ask one more question?
Yeah, sure.
So the question is on the last part of this presentation, your last presentation. So as I understood, the idea to have quick crystallization is to have a network. Am I right? To have a network in a amorphous state. So if we have a network, then we have quick crystallization. I think it's the last slide, or previous one might be. And the question is, do we need a network, or the rings, four-fold rings are essential, or it's both? And another part of the question is, could we understand these four-fold rings as a heterogeneous crystallization? I saw a word in your presentation that these are the precipitates for crystallization. Is that right? I'm sorry.
So sorry, I can't catch up. So
the question is, what you conclude that to have fast nucleation, crystallization, you need a network to be in amorphous.
Yeah.
Is that right? Or do you need the four-fold rings also?
Yeah, I think so. Because four-fold ring is a rock salt lattice, and so this is a important starting point, nuclei. So it is important point.
And the
because
second part.
This is consistent with the behavior of crystallization. So we can observe large amount of crystalline nuclei in the early stage of crystallization. This should be four-fold ring. And also network is important to sustain crystalline topology. This type of connectivity is also important for fast crystallization. And also antimony tellurium bond actually don't form network, but just if we expand the coordination distance, we can find network. That's the reason why we call pseudo network antimony tellurium. So antimony does not distribute randomly, and antimony tellurium correlation has crystalline topology in amorphous phase. But why distance is longer? Because density is lower in amorphous phase. So antimony tellurium correlation distance elongate in amorphous phase. But they have topology. That's the reason why this material can crystallize very fast. This is our conclusion.
I got it, but let me ask the second part of the question. Can we suppose the fourfold rings in amorphous structure as a precipitates for nucleation?
Yeah.
So these are like pre-nucleus in amorphous phase.
Mm-hmm. Yeah.
Thank you.
Any more questions, please? Okay, if we do not have additional questions, I'd like to thank our speakers for nice talks, Bob and Shinji.